So now we reach that crucial step where we ask, can we optimize our solution? Going back to our code here, we know that we have a time complexity of O of n squared and a space complexity of O of 1. The n squared is formed by our double for loop, and when we did this in our first array question, we were thinking of ways to increase our space in order to decrease our time. But we need to rationally think about this. Is that same approach going to help us here? And this is a very important thing because we need to actually think about what this question is asking us and how our solution attempts to solve it. What are we doing? We are storing the max area that we've come across so far of every area that we calculate using P1 and P2. So this double for loop does not separate because we need P1 and P2 together in order to figure out the area. And that's why we have no step in between these two for loops, which means that there's actually no additional caching that can happen for P1, this first for loop. What about the second for loop? Is there anything we can do with memory in order to improve this process or even eliminate this for loop as a whole? Well, what we do is we calculate the height and width using these two P's, and then we get the area. Then we essentially just check against the max area we've got so far, and we see if we need to update it. But there really is nothing here that we're doing that would consume more memory because the moment that we're done with this area, we don't need it anymore. If we needed it and it was greater than what we had, then we would have stored it already. But there's nothing here that we can do in order to scale our memory in order to improve this process. So what we did last time is not going to work here. And that's a very important thing because we need to really rationally think about this problem. So what we do need to do that can improve this is actually learn a new technique, which is known as shifting pointers. And let me show you what that is. So here I have generated a new test case for us, and I switched the pointers from P1 and P2 to A and B to better match what we have in our formula. And I want us to really think deeply. Now, this new test case will help us understand this new concept, but I also want to build upon the knowledge that we've gained so far from both our previous array question as well as what we've just done with our 2 pointers in our non-optimal solution. Let's first think back to our original array question, the very first one we did. If you remember, we were given some target value. Let's say using the same array, that value was 13. We know that when our first pointer is pointing at this value and our second pointer is pointing at this value, 4 and 9 add together to give us 13. And there we had our solution. The key difference here is that the distance between A and B didn't matter with that question. A and B being on the opposite sides of the array has no impact on how we come to the solution for finding our target. In fact, this is easily demonstrated that if our target changed to be 6, this means that in order for our solution to work, B needs to be in this place here. But this has no impact. A and B being anywhere in our array doesn't change how we find our target. But this is not the same case as our current question. We know that with our current question, the width has a direct impact on the actual area. We know that by looking at our equation, we can see immediately that the distance between A and B has a direct impact on the value of the area that comes out of it, because that's the nature of multiplication. The other thing we need to note, though, is that we don't really know whether or not it's increasing or decreasing that will change this area outcome, because it varies from a case-to-case basis. It's not a guarantee that as long as A and B are greater distance apart, then somehow our area goes up. That's not the case. We can actually see that directly in this current example. Let's do the calculation for the area now, using the placement of A and B right here. So the minimum between A and B is the minimum between 4 and 9. So 4 is the minimum value. As for B index minus A index, that's 5 minus 0, which gives us 5. So 4 times 5 gives us 20. But what happens if we move A forward by 1? So let's move A forward and do a new calculation. We'll keep the 20 as a reference. A moves forward to 8, and now we have to recalculate. The minimum between A and B, so 8 and 9, is 8. And B of I, which is 5, minus A of I, which is 1, is 5 minus 1, which gives us 4. 8 times 4 gives us 32. So automatically we can see that by shrinking the size of our width, we actually ended up with a larger area. So this leads us to our second point, which is that if we really think about what just happened, the outcome of the area is impacted by the lesser of the two values of A and B. We saw that by shrinking the distance between A and B, we somehow ended up with a larger area, which tells us that the only value in this part of the equation that has some impact on the outcome of the area is the smaller value. So let's just go back to what we had before. We saw earlier what happens if we were to move our smaller value. By increasing it, we saw a direct transformation where the area got bigger. But what about the larger value? What about B? Let's say we move B inwards. What are the only possibilities that could happen for B? Well, B either gets larger or it gets smaller. So let's explore these two cases. Let's say B got larger first. So instead of 3, just imagine it was 12. When we were to plug this into our area calculation, what happens to the min? It's still going to be 4 against 12, which means that the number that comes out of this is still 4. This means that even though B got bigger, there was no direct impact on our area calculation. So now we know that if the larger number gets larger, it doesn't matter. We don't even care about it. But what happens if the larger number gets smaller? So instead of, let's say, the 12, let's say it becomes the 3 in the place that it is right now. So now the calculation becomes the min of 4 and 3, and now our min changes. Our min becomes 3. So here we actually see that our area would have been smaller in this case, because not only did we decrease the value on this side, we've also decreased the value on this side. So we know that for the larger value, the only case is that by changing its placement, we have somehow decreased our total area. And we don't want that. We only want to figure out if we can maximize the area, if there's a way for us to increase the area possible. So now let's put these two ideas together. We know that the only thing that really matters when it comes to moving either A or B is trying to move the smaller value forward and try and see if that somehow yields us a larger calculation. And that's going to be the real crux of this optimal solution and this new technique, which is known as the two shifting pointers. So what we want to do is exactly what we have here. We want to initialize 2 pointers, but we want to initialize them at the opposite sides of the array. Because what we're doing is we're maximizing this value right here. We want to get the biggest calculation possible for width because it does have an impact. And we also want to make sure that as we shift our values, there's no possible way where the values on the outskirts, meaning the opposing sides of our variables, could possibly give us a larger container. So we just got to make sure of that. And how we make sure of that is just by starting on the ends. So now our calculation becomes, what is the smaller of these two values? We're going to calculate the area first of A and B. So we did this calculation already, but let's just do it again. But we're also going to keep track of the max area that we find so far. Very similar to what we did before. And let's just say it's max and which starts at 0. So the minimum between 4 and 9 is 4. And 5 minus 0, which is the indices, is 5. So 4 times 5 is 20. And that's bigger than our max area, so let's update that. Next, let's move A forward, because A is the smaller value, and as we mentioned, we only care about the smaller value. A moves forward, and now we get the min between 8 and 9. So this value is now 8. And the distance is 5 minus 1, which is 4. 8 times 4 is 32. And we have a new max area of 32. Now we have to shift the smaller over once more. So A comes over, and we do our calculation once again. The min between 1 and 9 is 1. 5 minus 2 is 3. The area here is 3. 3 is not bigger than 32, so nothing happens in terms of our max area, but we shift our values over again. And this time, we do our calculation the exact same as we did last time. The min between 2 and 9 is 2. The distance is 5 minus 3, which is 2. So this gives us an area of 4. 4 is still not larger than 32. So we do our A shift again, which is because it's the smaller number. And now the min between 3 and 9 is 3. B and A is 5 minus 4, which is 1. So once again, we get another container area of 3. 3 is still smaller than 32. So our max area now is done. We have no more room for any of our pointers to move because they've just come up against each other. So now we have our answer. 32 is our maximum area. The other thing that we'll notice is that we've also only touched each element once. This means that we've managed to bring our time complexity down to O of n, which is a drastic improvement from O of n squared. Every element will only be operated on once. And then after that, we are definitely moving one of our 2 pointers. We don't know which one, but one of them is moving, which means that at most we performed n operations on this array. So this is the thing about 2 pointers. The main key with the 2 pointers is that we have to think about how we move these 2 pointers, when it's considered done moving, and also what is the rationale between determining which of them to move in the first place. We were able to figure this out because we were able to see from our area calculation that the minimum value between these 2 was the only one that actually directly had an impact on an area getting bigger. The other thing was that we were able to see that the width had some factor to do with it, because in some ways, when the width changes, these 2 values must change. One of them has to change. So we just had to figure out which one of them to change, and by looking at this minimum value and how it affects the area, we could see that by moving the minimum value, that was how we could possibly end up with a larger area. So then the optimization just became, okay, let's shrink our width on every operation, but then conditionally based on which value was smaller would be the one that we shrunk. And along the way, we just calculate the area and store the max area the way that we've been doing before. So I know that a lot of that is really new knowledge. And this process of breaking down this equation into the rational steps to do this is going to be one of the key things in critical thinking that we need to work on. And really thinking deeply about these things that seem at first very basic. Because within them lie the chance for optimization when combined with these technical tricks such as this 2-pointer style of problem solving. And this course is really going to focus on these 2 things. We're going to learn some of these technical tools that we just saw with the 2 pointers, but also how do we build up a mental framework so that we can rationally break down what the rules are and how we can best utilize these tools in order to deliver us an optimal solution. So what I want you to do now is take what we've just seen and try and code it yourself. It's going to be a little different from what we did with the for loops, but it's still good to give it a try. If you can't figure out how to do it, no problem. That's what we're going to do in the next video.